Organic multi-step synthesis reactions. During the first semester organic labs, this transformation was carried out. Stilbene was converted to 1,2-diphenylethanone, but this can't be done in a single step. It required multiple steps. First, stilbene was brominated in an electrophilic addition reaction to 1,2-dibromo 1,2-diphenylethane. Then 1,2-dibromo 1,2-diphenylethane undergoes double dehydrohalogenation with 2 moles of KOH to produce diphenylacetylene. And then finally, the alkyne is hydrated using mercury catalyzed hydration. Mercury 2-sulfate and sulfuric acid and some water hydrates it to an enol, which spontaneously rearranges to a ketone. To convert a starting material, that is a precursor, into a product, a target molecule, it often requires several steps. And multi-step organic synthesis is an everyday occurrence in both chemical industry and chemical research. Indeed, almost all organic products, pharmaceuticals, personal care products, plastics, etc., are produced from starting materials such as petroleum or plant extracts, and these bear little resemblance to the final product. Many job descriptions for organic chemists stress the importance of skill in planning and carrying out multi-step organic synthesis. In order to plan multi-step synthesis reactions, one must become familiar with a large number of classic organic reactions. And as usual, practice is the best teacher. When you're planning a multi-step reaction, you need to think both backwards as well as forwards. For example, look at the final product and ask yourself, what is or what are the immediate precursors to this product? At the same time, consider how the starting material can be converted into one of the intermediates. I have a dozen or so problems here that require multi-step synthesis reactions. Let's get some practice working through these. In the first example, we have 2-bromo 3-methylbutane being converted to 2-bromo 2-methylbutane. Now, we didn't study any reaction that would simply move a halogen and hydrogen and exchange places. This has to be done in more than one step. What we have learned in this chapter on alkenes is how to prepare an alkene and then how to react an alkene. What we can do is convert this halide to an alkene and then convert the alkene to the other halide. So how do we convert an alkyl halide to an alkene? Before we begin, let me point out to you that in the appendix on page 163 there is a summary of the reactions and preparations of alkenes. This runs over onto the next page. This is not a good way to study. The best way to study is to learn the mechanisms, but by way of review this is very helpful and you can quickly sort through the various reactions and preparations of alkenes as you answer these questions. Alright, so what we'll need to do here is convert our starting material, alkyl halide, into an alkene, and then we can convert the alkene to our final product. So how do we convert an alkyl halide into an alkene? Recall that a secondary or tertiary alkyl halide, what is the degree of substitution on this alkyl halide? It's secondary because the carbon bonded to the halogen is bonded to 2 other carbons, so this will undergo an elimination reaction. If I use KOH, strong base, typically ethanol as a solvent, and we'll lose HBr, elimination. How does that work again? I want to point out to you, you're not required to show mechanisms in these multi-step reactions, but I may discuss them with you just to remind you of them as we do it. Here's the alpha carbon is the carbon bonded to the functional group, and beta carbons are those immediately adjacent, so there's beta carbons on either side. In this concerted reaction, the halide leaves at the same time as the hydroxide removes the hydrogen ion, and the pair electrons fall back and form the pi bond. Now this could happen from either the right side or the left side of the alpha carbon, but recall Zaitsev rule says that the more stable, more substituted alkene is formed, so it's the one I'm showing on the left that will form. And that'll give us our intermediate. And this is 2-methyl-2-butene, or 2-methyl-but-2-ene. And this alkene can be converted to an alkyl halide. So now if we add HBr, it will add across the pi bond, giving us the alkyl halide. But will it give us the one we want? Let's think through the mechanism. The pi bond is a nucleophile, an electron donor, and the hydrogen in the HBr is an electrophile. So the pi bond breaks, forms a bond to the hydrogen, bromide leaves with a pair of electrons. The hydrogen will add to the less substituted carbon, producing a carbocation here on the more stable, more substituted carbocation. It will be tertiary. And then the bromide will add to that carbon. So in fact, that will give us the product we're looking for, 2-bromo, 2-methylbutane. Let's try the next one. Again, we start with an alkyl halide, but this time we're starting with the product from the previous reaction. This is 2-bromo, 2-methylbutane. We want to form 2-bromo, 3-methylbutane. Well, again, we can use KOH to start the reaction, form the alkene, this is a tertiary alkyl halide, so no problem for an elimination reaction to occur. Once again, the halide is lost from the alpha carbon, and hydrogen ion lost from the beta carbon, and the pi bond forms in between the two. The more stable, more substituted Zaitsev product forms. This is the same alkene as previously, 2-methyl-2-butene. Now if we simply add HBr, what product would we get? Think about it. The pi bond breaks and forms a bond with the hydrogen. The hydrogen adds to the less substituted carbon. Carbocation is here, then bromide adds. Well, that takes us right back to our starting material, so that's not going to work. How do we get the bromine in the anti-Markovnikov position? Do you recall that when you add hydrogen peroxide first with the hydrogen bromide, it forms bromine free radicals? Free radicals are very reactive. They are the electrophiles. When the pi bond breaks, bromine adds first instead of hydrogen. Bromine adds to the less substituted carbon, and then hydrogen adds second to the more substituted carbon, and that will give us our anti-Markovnikov product. Page 102. Our first problem shows the conversion of 1-propanol to 2-propanol. You're not responsible for the nomenclature of alcohols in this course. That'll be later. But I will take every opportunity to present it to you in any case. Now we have no reaction we've studied that would convert one alcohol to another, but we have learned that we can dehydrate alcohols to alkenes. We do that with concentrated phosphoric or sulfuric acid and some heat, losing water. Do you recall how that works? The hydroxyl group is protonated by the acid, forming water. Upon heating, the water leaves, forming a carbocation. This would be a primary carbocation, so it would rearrange by a hydride shift and form a secondary carbocation. And then a hydrogen ion is removed by a water molecule from one of the adjacent carbons, either end. In either case, a single product will be formed because this molecule has a simple structure. We'll form propene. Can we convert propene to an alcohol? Well, isn't that hydration? Sure it is. How do we hydrate? We add aqueous acid, such as sulfuric acid typically, a little bit of heat. And how does that work? Well, the alkene carbon, the pi bond, is a nucleophile, It'll be protonated by the hydrogen in hydronium ion formed by the aqueous sulfuric acid. So hydrogen ion adds here, the carbocation forms here, then water adds next, water finally deprotonates and we get 2-propanol. Let's try the next one. This is 2-propanol. We want to convert this into 1-propanol. Can't do that in one step. Let's first dehydrate the alcohol. Concentrated sulfuric or phosphoric with heat, losing water. We form propene. Can we convert this alkene to an alcohol? Well, the first thought might be to add dilute aqueous acid, in other words, hydronium ion. What would happen if we did that? The hydrogen ion would add to the less substituted carbon. Carbocation is here. Water would add here. So we wind up back with our starting material. That's not the right reagent. We need, in fact, the anti-Markovnik alcohol. How do we add the water to the less substituted carbon? There was a set of reagents that did that. Do you recall? If we used borane gas, bubbled into our alkene in a non-aqueous solvent like tetrahydrofuran, followed by hydrogen peroxide in basic solution, the borane adds first. Now, remember that boron is in group 3A. It's a subvalent compound. Boron has an empty 2pz orbital. It's certainly electrophilic. And here's our nucleophile. The BH3 adds such that hydrogen will add to the more substituted carbon because it's more crowded here and hydrogen is small. Simultaneously, BH2 adds to the less substituted carbon because there's more room here and BH2 is larger. That'll put the hydrogen on the central carbon and BH2 on the end carbon. In the second step, hydroxyl group from our peroxide displaces the BH2, giving us the anti-Markovnikov alcohol, 1-propanol. Let's try the next one. We're starting with cyclopentanol, and we're going to 1,2-cyclopentane diol. Notice the hydroxyl groups are on the same side. Therefore, this would be cis 1,2-cyclopentane diol. Again, that can't be done directly, so we'll need to do it in several steps. We know that we can dehydrate alcohols using concentrated acids like sulfuric or phosphoric and heat, losing water. The hydroxyl group is lost from one carbon and a hydrogen from an adjacent carbon. We can rotate this to make it look more of what we need. Let's put the double bond here. Same thing. We need to convert cyclopentene to cyclopentane diol. Notice the pi bond is gone and we gain 2 hydroxyl groups. This has to be an oxidation. The pi bond breaking, but not the sigma bond. It must be a mild oxidation. Do you recall that cold permanganate in neutral or basic solution will cleave the pi bond but not the sigma bond and add hydroxyl groups to the same side? That's it. Let's try the next one. This is cyclopentyl chloride or chlorocyclopentane in IUPAC. we need to convert it to E 2-bromo cyclopentanol. We can't do it directly. We can, however, dehydrohalogenate this secondary alkyl halide using strong base in ethanol. The chloride leaves from the alpha carbon and a hydrogen from one of the beta carbons, giving us cyclopentane. To convert cyclopentane to this bromo alcohol, this halo alcohol or halohydrin, it's going to require the addition of bromine in water. Bromine is electrophilic, and it will add first, here's our electron donor to the bromine. Bromine adds, then forms a bromonium ion intermediate. Now, when bromine adds, bromide is a leaving group, and it's a good nucleophile. So it can add and get a dihalide. However, in aqueous solution, recall that saturated bromine water is only 4% bromine. It means 96% of it is water. So there's a lot more water molecules than bromide nucleophiles. And even though water is not a very good nucleophile, it's only classed as fair, it simply outnumbers the bromide. And so by sheer probability, it'll be hydroxyl that adds after bromine, giving us this trans Vic haloalcohol. Let's try the next one. Here we start with cyclobutanol. We're going to this dicarboxylic acid with 4 carbons. This is called butane dioic acid. Again, we can't do that directly, but we could dehydrate this alcohol to an alkene using concentrated sulfuric or phosphoric acid and some heat, losing water. Hydroxide is lost from 1 carbon and then hydrogen from an adjacent carbon. We'll get cyclobutene. Now when you're doing multi-step reactions, it's helpful to note how many carbons you start with and how many carbons you finish with. In this case, we're starting with 4 carbons and we're ending with 4 carbons. So we haven't gained or lost any carbons. What's happening in this reaction, the sigma and pi bond are broken so that the ring opens up and we're gaining oxygen. So clearly this is an oxidation. We studied that hot potassium permanganate in acidic solution will cleave sigma and pi bond. The carbon, which is bonded to 1 hydrogen and 1 other carbon here, will be oxidized to a carboxylic acid. The same is true on the opposite side. And that'll give us butane dioic acid. Page 103. Here we're going to convert 2-methyl cyclohexanol into 1,2-dibromo 1-methyl cyclohexane. Notice that the stereochemistry is shown. The higher priority groups are on the opposite side of the ring. This will be E, 1,2-dibromo, 1-methylcyclohexane. How will we convert the alcohol to the dihalide? Well, not in one step, but what we can do, using concentrated acids such as H2SO4 and some heat, we lose water. We'll dehydrate the alcohol to an alkene. Notice that the more stable, more substituted Zaitsev product is formed as the major product. Recall the mechanism of dehydration. The hydroxyl group will be protonated by hydrogen ion from the acid. It will leave as a neutral water molecule, taking this pair of electrons with it. That'll form a carbocation in this carbon. However, adjacent to it is a tertiary carbon with a hydrogen on it, and so there'll be a hydride shift from the tertiary carbon to here. We'll have a second hydrogen here, and the carbocation will form on the tertiary carbon. In the final step, hydrogen ion is removed from an adjacent carbon, and this pair of electrons falls back to form the pi bond. And that will give us 1-methyl cyclohexene. And how do we convert 1-methyl cyclohexene to E, 1,2-dibromo, 1-methylcyclohexane? This is a trans-Vic dihalide. That is formed by bromination of an alkene using a non-aqueous solvent. Do you recall how that works? Here's our nucleophile. Bromine is the electrophile. The pi bond will form a bond to the bromine. Bromine will add to the less substituted carbon, carbocation on the more substituted carbon, but the bromine will form a bromonium ion bridge to stabilize the carbocation. The leaving group bromide will then add to the carbon that was the carbocation, breaking the bridge. It adds from the opposite side, giving us the trans-Vic dihalide. In the next problem, we have 2-bromopropane going to this bisulfate. This is isopropyl bisulfate. Again, we can't do it in a single step, but we certainly can dehydrohalogenate this secondary alkyl halide using KOH in ethanol, losing HBr, giving us an alkene. Propene. To convert the propene to the bisulfate, we simply need to add conc sulfuric acid. No water. The hydrogen will add to the less substituted carbon first, because here's our nucleophile, our electron donor, and then the only nucleophile remaining is bisulfate ion. Even though it's very weak, it'll add to the carbocation, giving us our product. Here we have 1-bromo, 1-methyl cyclopentane. And we're going to convert that to 1-bromo, 2-methyl cyclopentane. Again, we can't do it in a single step, but what can we do? Well, we could dehydrohalogenate minus HBr using a strong base KOH in ethanol. So we have a hydrogen on the beta carbon, and there are 2 beta carbons, but you see they're identical. Here's the alpha carbon, that's beta and beta. In either case, the loss of bromide from the alpha carbon and one of the hydrogen's ions from the beta carbon. This becomes a new pi bond. Will give us the alkene. Our methyl group is still there. Here's our alkene. Let's rotate this around a little bit here. Okay. I want to convert this to our product. If we simply add HBr, what will we get? The hydrogen ion will add to the less substituted carbon, forming the more stable, more substituted carbocation to which the bromide would add, which brings us back to our starting material. That won't work. We need an anti-Markovnikov addition. This can be done with HBr if we also add hydrogen peroxide, which produces bromine free radicals. The bromine free radical is electrophilic. It adds first to the less substituted carbon here where we want it, and then hydrogen adds here. In this last reaction, we want to convert 1 phenylethanol to this aromatic carboxylate. The name of this is called benzoate. How are we going to do that? Well, certainly not in one step, so let's do what we can do. Let's dehydrate this secondary alcohol using concentrated acid. So the hydroxide will be lost, and a hydrogen from a beta carbon that has to come from here. Bear in mind there are no hydrogens. This carbon already has 4 bonds. So our product of dehydration is going to be, this is called phenylethene. There's several common names in use. It's also called vinyl benzene, if you recognize the vinyl group. And we also have styrene is another common name for this. In any case, how are we going to get it from phenylethene to benzoate? One of the things you want to take note of is that we're losing a carbon. Notice that the product has aromatic carbonyl, just 1 carbon, so that means this carbon must be cleaved. What reactions did we see that caused cleavage? Mostly oxidations, and in fact you see that the product is oxidized. It's got 2 more oxygens. So for that we're going to need hot potassium permanganate. Now if it's an acidic solution, we would get a carboxylic acid. It would look like this. And the carbon on the right is just CH2. That'll go to CO2. We won't concern ourselves with that. But the product isn't an acid. In fact, it's the basic form. So that must mean we must have used hydroxide ion. In other words, permanganate, hot, in basic solution. And that would deprotonate the acid after being formed to give us the carboxylate. And finally, page 104, only 2 problems left. This is 1 bromo, 1 methyl, cyclopentane, and our product will be 1 methyl cyclopentane. Certainly we can't simply remove a bromine by itself. How can we start this? Well, this is a tertiary alkyl halide, so we can bring about dehydrohalogenation, losing HBr by adding a strong base, KOH, in ethanol. So in this process, the hydrogen from one of the beta carbons, let's say it's here, the hydrogen ion is removed, the pair of electrons left behind becomes a new pi bond, and bromine leaves with the pair of electrons as bromide. And that's the elimination reaction. Here's our product. This would be 1-methyl cyclopentane. We need to convert that to 1-methyl cyclopentane. Oh, well, that's easy. All we need to do here is saturate the alkene to an alkane. We do that with hydrogen on a variety of catalysts, such as nickel or palladium or platinum and such. Okay, here's the last one. This will be 1-methyl cyclobutanol. And this monster here, 1, 2, 3, 4, 5, 6, you'll learn how to name these later. It's got a ketone group and an aldehyde. The aldehyde has precedence, so it's named as an aldehyde. It's going to be hexanal. And it has an oxo group on the 5th carbon. This is 5-oxo hexanal, Al for aldehyde. Don't worry about the nomenclature here. But how will we do the transformation? Well, certainly not in one step, so let's do what we can do. Let's dehydrate the alcohol. We use concentrated phosphoric or sulfuric acid and heat to lose water. In the dehydration, the hydroxyl group is protonated, then it leaves with the pair of electrons, forms a carbocation, and then a hydrogen ion is removed from one of the adjacent carbons. The pair of electrons remains behind to form the alkene. So let's draw our product. And let's say that would be our product. That would be 1-methyl cyclopentane. And we want to produce 5-oxohexanal. Well, notice the number of carbons hasn't changed. We have 5 in the ring plus 1 is 6, and our open chain structure has 6 as well. So all we need to do here is cleave the sigma and pi bond to open the ring. And we'll need to oxidize these alkene carbons to the ketone aldehyde groups. If you recall, a 2-step process, ozone at minus 78 degrees C, that's the sublimation temperature of dry ice, in some kind of nonpolar solvent like dichloromethane, followed by zinc in acetic acid. We'll cleave the sigma and pi bond, and this carbon here, which is bonded only to carbon, becomes an aldehyde group, which you see here. And then this alkene carbon, which has 1 hydrogen on it, becomes the aldehyde group, which you see here. And that's it for multi-step reactions of alkenes.